Hello, welcome to my channel. We are studying current electricity and we have read about Ohm's law, limitations of Ohm's law. Today I will discuss the drift velocity as the conductor is connected with the battery, then the small constant velocity that is superposed on the random high speed of the all zigzag motion doing electrons. Its relation, that is drift velocity, its relation with current and potential difference. Why? Because if current flow through a conductor, that means some charge is flowing per second through a conductor, because current is rate of flow of charge. So all the free electrons in case of conductor, they are going opposite to the electric field with the very small velocity, drift velocity. How are they? This drift velocity is related with the current and the potential difference applied. Let us start that if a conductor of length A and cross sectional area, length L and cross sectional area A is connected with the ends of the battery of potential difference V. This is plus, this is minus. So current flow through the conductor like this. Now, if through any of the cross sectional area the charge flow is given by Q, that is the Q is the amount of charge flowing through the conductor at any point, from any point, through any cross sectional area, then this charge you can write here that charge is NE. But what is N? Number of electrons, free electrons per unit volume. So the net charge flowing through the conductor, how can you write this? Multiply A into length. So this NaL will be the net number of free electrons flowing through the conductor, and free electrons number into charge you can write electronic charge, that is the total charge flowing. What is the current through a conductor? I is Q by T, rate of flow of charge. So in this way we can find the value of I. Now what happens that the electron, free electron, this is the direction of electric field, then free electron drifts with the velocity Vd. Suppose it covers the whole length L in time t. Then what can you write Vd? Vd as the electron covers L distance in time t. So in place of L, what can you write? L as Vd into T. Therefore, you can write here this N A Vd into T into E, this is upon T, and this expression is for I, that is I equal to N E A Vd. This relation says that the current through the conductor and this Vd, how are they related? Next, suppose the battery is of potential difference V, and we have read the Vd is given, that is drift velocity is also given by the acceleration into average collision time. This is called relaxation time. And what is A here? This is E electric field, electronic charge upon m into tau. So E electric field of this battery, which is electric field is established along the conductor, can be written as E equal to V by L, that is this magnitude of electric field. So we can write E V upon ml as tau into tau as Vd. This drift velocity. From this relation, we can find that what is the potential difference and drift velocity relation. So, what is V here? This is ml Vd upon what is here? E tau. Now, this expression says the potential difference, and this is for the current flowing through the conductor, and we know that what is V upon I. V upon I is R. So, what is the resistance of this conductor? It can be obtained by dividing the equation of V with the I. So, you will get V upon I as what is V? M L upon this Vd, and this Vd will be cancelled. E tau, what will you get? N, this will become E square A, this will, and this is tau. So, this is tau. So, this ml upon n E square A tau is called, expressed as, because V upon I, what is R? So, this is also expressed as R, that is resistance of conductor. Earlier you have read that resistance is given by rho L by A. What does it mean? That resistivity and resistance, how are they related? So, if you compare this relation for resistance with the rho L by A, we can also conclude that rho is, put L upon A separately, what is left here? M upon n E square tau. What is M? Mass of electron. This number density, number of free electrons per unit volume, and total number of free electrons, this is electronic charge, and this is average relaxation time. So, what we observe, that we have previously said that rho is independent of length and area of cross section of the conductor, and it is quite clear here that in this expression there is no length and no area of cross section. It solely depends on two things. Number one, nature, that is conductor, then large number of free electrons, semiconductor lesser, insulator very few, negligible, and temperature. How temperature? That if temperature is increased, collisions will increase, so tau will decrease. While R, look in the R, this nature and temperature, it is dependent. Also, it is directly proportional to the length and inversely proportional to the area of cross section. So, resistance of the conductor depends on its length and area of cross section, and nature and temperature. One more expression we can find here, that if I equal to NEAVD, then what can you write for I upon A? What is I upon A? This is current density J, that is current flowing through unit area perpendicular to it in a conductor. From its conductor, the current flowing is, current density is J. So, what can you write J? This make I upon A. You will get NE into Vd. For free electrons, this electron, they flow opposite to the electric field, and electronic charge for free electrons, negative charge electrons having. So, this J is written as minus NE into Vd. So, how drift velocity and current density is related? This is the expression. Now, if resistivity is known, then how can you write resistivity in terms of current density and electric field, or 1 upon resistivity, inverse of resistivity is conductivity. So, there is a relation also in between current density and electric field. How? Just now you have derived that V, that is potential difference. what you have derived earlier, that V is given by, suppose it start with the Vd. You know Vd is A tau, this is. And what is A? If you write A, so this is E upon m into tau. What is E upon m into tau is Vd, and Vd you can also write from the equation I equal to NEA Vd. Then what can you write Vd? As I upon NEA. So we can write here this I upon NEA equal to E tau upon m. That is, we have equated the Vd from A tau and from this relation. You know I upon A is current density, so you can write here J. And here this E is, suppose you left E and transfer the NEA on the right hand side. So what will you get? NE square A upon m into tau. This can be written as this J equal to, this is NE square tau upon m into E. Look that this the quantity, these NE square tau upon m written in bracket is just reverse of resistivity. What is the name of this? Reverse of resistivity is conductivity. So you can write that this J equal to, this is sigma, that is conductivity into electric field. And this is the relation which shows the vector form of Ohm's law, because this J is vector, current density, and electric field is also vector. What does it mean? That this current density, that is, if the current is flowing through a conductor, then at any point the current density is found to be directly proportional to the electric field if the J and E have the same direction. This is also called the microscopic form of Ohm's law or vector form of Ohm's law, because J and E are vectors. So in this way, another point for vector form of Ohm's law you have seen here. Now how the resistance, this is written here, it depends on the temperature. So let us discuss the temperature dependence of a resistance. Temperature dependence of resistance Let us start for metal. What happens in case of metal? There are large number of free electrons and they move through the conductor opposite to the electric field when electric field is applied across the ends of it. What happens that in case of metals, there are large number of free electrons, and suppose the R for a conductor metal is given by this relation. Now here M is constant mass of electron, charge on electron, area of cross section, length, and suppose for a particular metal N is also very large. The relation other than the term here other than constant is this tau, which depends on temperature. You know, when the temperature is increased, then collisions, number of collisions also increase. So this average relaxation time decreases. So what can you say? That R is can be written as inversely proportional to the temperature. So if R is inversely proportional to the temperature, then what is evident from this relation? That if temperature increases, then what happens? This relaxation time decreases therefore R of metal, that is resistance of metal, increases. Now, if we apply the same for, we can say the resistivity, then resistivity is also shown that if you take temperature here at the x axis and resistivity on y axis. Then in case of metals, this is the graph which shows that for the low value of temperature, the resistivity is, suppose this is rho naught, that is at the 0 Celsius. Due to thermal collisions, the free electrons collide, and therefore this is the very less value, but it is rho naught is represented at 0 degree Celsius, the resistivity of metals. And after certain finite value, very small finite value, it has been found that this increases linearly. How? It has been observed that the resistance of a conductor is given by R naught at 0 degree Celsius and RT at T degree Celsius, then RT equal to R naught 1 plus alpha delta T. This R naught is temperature at 0 degree Celsius, this RT is temperature at T degree Celsius, this alpha is called temperature coefficient of resistance, and this delta T is the change of temperature. So, we find that if change of temperature is suppose 1 degree Celsius and R naught, that is resistance at 0 degree Celsius, is 1 ohm, then what can you write here? This alpha can be written as RT minus R naught upon R naught into delta T. These are ones. R naught is 1 and delta T is 1 degree Celsius. Then how will you define this temperature coefficient of resistance? It is equal to the change in resistance when from value of temperature of resistance, that is the temperature increase in resistance is made only 1 degree Celsius from 0 degree Celsius. Normally for metals, it is found alpha is 1 upon 273 degree Celsius per degree Celsius, 1 upon 273. If we put here this value, then what will you get? This R naught, RT will become R naught 1 plus T upon 273, and you know that it can be written as R naught capital T, that is in Kelvin, absolute temperature, upon 273. So, what we observe here from this relation, that this RT is directly proportional to absolute temperature. So, from very less value, initially 0 Kelvin, then resistivity due to thermal collisions is very nominal value. After that, we find that at higher temperature, this resistivity is almost directly proportional to T. So, in case of metals, how the resistivity or resistance increases with temperature, it is explained here. Now, in the next video, I will explain the effect of temperature on the semiconductor, electrolyte and alloys resistivity, how these resistivities vary. Okay. Thank you.